Welcome to the Overview Effect. Today we're looking at what is honestly a fundamental mystery of artificial intelligence. I mean, think about it. How exactly does a machine resolve the endless, constantly shifting ambiguity of human language without actually knowing any real grammar rules? You see, large language models like ChatGPT, they're essentially just deep neural networks that generate text one single word at a time. But here's the catch. To predict the next word accurately, they have to deeply understand the context of everything that came before it. And human language? Well, it is notoriously, beautifully messy.
Okay, let's dive into this with a quick little test. Take a look at the sentence on the left. The trophy did not fit into the suitcase because it was too large. What does the word "it" refer to there? Instantly, without even trying, your brain knows it refers to the trophy. Now read the sentence on the right. The trophy did not fit into the suitcase because it was too small. Suddenly, literally in the blink of an eye, the exact same word "it" refers to the suitcase. This right here is what we call the ambiguity trap. As humans, we resolve this shifting meaning instantly, right? We just use our common sense and our basic understanding of physical space. But computers absolutely do not have common sense. All they have is math.
So to really understand how a machine beats this ambiguity, we first have to talk about something called the static coordinate problem. And this brilliantly illustrates what happens under the hood. To solve the language puzzle, the machine has to map our human words into a vast mathematical universe. It takes a simple token, basically a piece of a word, and assigns it a massive multi-dimensional coordinate. But here is the massive roadblock. A static coordinate is completely inadequate for actual fluent reading. Think about it. In total isolation, a rigid dictionary definition inside a machine is kind of like a dead star. Sure, it possesses a fixed static identity, but it totally lacks life. It has absolutely no idea what is happening around it. But deep inside the GPT model, within what we call the transformer block, there's a specific module called masked multi-head attention. Now, I know that sounds like a bunch of complicated jargon, but it is actually the exact mathematical sequence that creates artificial comprehension. It's the engine that gives the model selective access to the entire input sequence at once, allowing it to dynamically pay attention to different parts of the text when it's making its predictions. So, to make sense of a highly ambiguous word like "it," the machine has to do something incredible. It needs to blend the original, static definition of the word with the immediate living context of the sentence around it. To achieve this, the machine must construct a brand new coordinate entirely on the fly. It calculates what we call a context vector. You can think of a context vector as a heavily enriched coordinate. It still contains the core of a word's original meaning, but it's been heavily altered by the mathematical influence, almost like the gravitational pull, of its neighbors. The machine absolutely depends on this gravitational pull from the surrounding words to form a cohesive, flowing thought. But building this enriched coordinate, that's where the machine faces a profound mathematical hurdle. Because out of an entire paragraph of text, what actually matters right now? It essentially has to stop and ask itself, how much influence should every other word exert on the current word? If it's desperately trying to decode the word "it," does the word suitcase matter more in this exact moment, or does the word large matter more? This precise question is the absolute core of the attention mechanism.
Which brings us nicely to how the machine actually measures that alignment.
The machine kicks off its calculation by making one specific word its primary focus, let's say our ambiguous pronoun "it." To test how strongly this focus word aligns with all the other words around it, it executes what's known as a dot product. Now, a dot product is a fundamental mathematical operation that measures exactly how tightly two separate geometric vectors align in physical space. The machine literally uses this operation to test the physical angle between the coordinate of the focus word and the coordinates of the rest of the sentence. This is how it figures out exactly how much attention to pay to each surrounding token. A great way to visualize this is to think of these coordinates like highly directional flashlights in a pitch-black room. If two flashlights point in the exact same direction, their beams overlap beautifully and the resulting light is blindingly bright. In math terms, that equals a massive alignment score. On the flip side, if they point completely perpendicular to each other, the beams cross without mixing at all. The resulting overlap is absolute zero. Now, because of how our initial linguistic map was built during training, words with similar dictionary meanings naturally point in similar directions. So the flashlight for suitcase and the flashlight for backpack, they overlap brilliantly. Now, what's really interesting about this slide is that it shows a structural dead end for artificial thought. Take a look at this sentence. The tiny puppy completely destroyed the massive sofa. In a standard static dictionary map, the concepts of a puppy and a sofa are complete geometric strangers. They point in entirely different mathematical directions. So if the machine just checks the raw dot product between them, the alignment is going to be terrible. It would completely ignore the connection between the two words and fail to realize that in this specific chaotic moment, the puppy is the specific agent causing the destruction. So here is the harsh reality. If the machine relies purely on its static dictionary definitions, it completely misses the hidden, invisible grammar of a specific sentence. It would just see a random pile of disconnected words. So, we had to teach the machine how to hallucinate grammar on the fly.
To do that, we introduced three very special concepts: query, key, and value.
In order to break the rigid rules of the dictionary and dynamically warp its geometric map based on the immediate context, engineers created three completely new filters. These filters are called trainable weight matrices. A trainable weight matrix is essentially a massive grid of adjustable numbers that mathematically transforms a word's original coordinate into a brand new shape. By the way, these are the parameters you're hearing about when people casually mention that a model has billions of parameters. Every single word in a sentence is forced through these matrices, splitting it into three completely different geometric avatars. These three avatars are known as the query, the key, and the value. To picture this, imagine you're standing inside a massive, endlessly sprawling library. The query represents the specific contextual gap that the current word is actively trying to fill. It's literally what you type into the library's search bar. It mathematically asks the system, what specific related concepts am I currently looking for? The key, on the other hand, is like the library's database index, used for searching. It represents what context the target word actually holds. And the value? Well, that is the actual book you pull off the shelf. It is the final conceptual shape that will eventually be extracted. Next up, the machine has to make sense of all these overlapping connections using the softmax filter. So the crucial point is that after measuring the exact physical angle between the query and the key using our dot product, the machine generates a raw alignment score for every single word. But these raw numbers, they're noisy, they're messy. To achieve absolute clarity, we have to apply a sophisticated mathematical filter called softmax. Softmax is a rigorous mathematical function that aggressively exaggerates large numbers and completely crushes small numbers right down towards zero. By applying this exponential curve, the filter demands decisiveness. It ruthlessly kills the noise, it forces the machine to choose a primary focus and ignore the irrelevant background words, perfectly distributing that 100% of its attention across the entire sentence. And that brings us to the actual geometry of grammar. Let's move to and see how this builds into actual comprehension. Once the machine knows exactly what percentage of attention to pay to each word, it scales those value vectors accordingly. For instance, it might take 80% of the value shape for puppy and maybe only 15% of the value shape for sofa. Then it mathematically stacks all of these shrunken, modified value shapes right on top of one another. They physically fuse into a single, brand new, highly complex coordinate, which is our final context vector. And here's the wild part. To build an artificial mind, the computer cannot calculate these fractions one by one in a slow loop. That would take centuries of computing time. Instead, the machine uses heavy matrix multiplication. It calculates the geometry for every single word in the sentence simultaneously. It multiplies the entire grid of attention weights by the entire grid of value vectors in one massive instantaneous mathematical strike. This insane parallel processing is exactly what makes the transformer architecture so powerful, and it completely solves our initial ambiguity trap. Think back to it. When the machine looks at the word it in our very first example, it generates a query. That query acts as a searchlight, aggressively scanning for nouns that fit the context of too small. The machine, remember, does not actually know what a suitcase is. It has no physical concept of what a trophy is. Through billions upon billions of rounds of training, it merely learned how to warp its key matrices so that the correct context lights up brilliantly, while the incorrect context stays perfectly dark. It is quite literally just bending geometric space until the correct answers physically collide with each other.
So, what does this all mean? It means that grammar is not some rigid set of human rules encoded into a machine. Grammar is just the optimal geometry for transferring information.
When you really look past the illusion of a machine reading a sentence, you realize that comprehension is just the beautiful optimization of geometric space. If this explainer shifted your perspective on how artificial intelligence actually thinks, make sure to subscribe to the overview effect, because if a machine can hallucinate something as complex as grammar just by bending math, What other human traits are just equations waiting to be solved? Thanks for watching, and we'll see you